Chapter 1.2, AI Workstation and Tooling. In Chapter 1.2, AI Workstation and Tooling, we focus on the environment that makes the rest of the course possible. Before we collect data, prepare datasets, train models, evaluate performance, align to Chapter 1.2, AI Workstation and Tooling in the Foundations section. ION and Tooling. In Chapter 1.2, AI Workstation and Tooling, we focus on the environment that makes the rest of the course possible. Before we collect data, prepare datasets, train models, evaluate performance, store artifacts, or expose inference APIs, we need a reliable workstation that supports modern AI engineering work. This chapter is still part of the Foundations phase. The purpose is not to install tools for the sake of installing tools. The purpose is to create a development environment where experiments are reproducible, notebooks are easy to run, dependencies are controlled, code is versioned, and the same workflow can eventually move from a local machine toward production. A poorly configured AI workstation can slow down an entire project. Many early machine learning problems are not actually model problems, they are environment problems. A notebook fails because the wrong Python interpreter is selected. A package works on one machine but not another. A model trains locally but fails in a clean environment because dependencies were never documented. A library upgrade changes behavior unexpectedly. A GPU is available, but the installed framework cannot use it. These issues are not glamorous, but they are very real. A professional AI workflow begins by reducing that kind of friction. At the center of the workstation is Python. Python has become the dominant language for data science, machine learning, deep learning, and modern AI tooling because of its ecosystem. Pandas, NumPy, scikit-learn, PyTorch, FastAPI MLflow, Hugging Face libraries, and many other important tools all provide strong Python support. This makes Python the practical glue that connects data work, model training, experimentation, inference, and application integration. The next important part of the environment is the code editor. In this course, Visual Studio Code is a natural choice because it works well across notebooks, Python projects, APIs, Git repositories, virtual environments, containers, and cloud-oriented workflows. The editor is not the intelligence of the system, but it is the place where the engineering work happens. A good editor makes it easier to inspect code, navigate projects, run notebooks, debug problems, manage dependencies, and structure a solution that can grow beyond experimentation. Jupyter Notebook is equally important, but for a different reason. Notebooks are not traditional applications. They are interactive workspaces where code, output, charts, observations, and explanations can live together. This makes them extremely useful during exploration. When we begin working with property data for the real estate valuation platform, we will not immediately build an API or production service. First, we need to inspect the dataset, understand the columns, look at example rows, visualize distributions, and test assumptions. Jupyter is ideal for that style of iterative investigation. A good way to think about it is this. Notebooks are the laboratory, while the application code base is the production workshop. In the laboratory, we explore, experiment, visualize, and learn. In the production workshop, we organize, package, test, and expose capabilities for others to use. Both are valuable, but they serve different purposes. Pandas is one of the first libraries we will use heavily. It gives us the data frame, which is the central table-like structure used for working with structured data in Python. In the real estate valuation platform, Pandas will help us load housing datasets, inspect columns, handle missing values, filter records, create derived features, calculate statistics, and prepare training-ready data. For tabular machine learning, Pandas is one of the most practical tools in the entire stack. NumPy supports much of the numerical work underneath the surface. Many machine learning libraries rely on arrays, matrices, and efficient numerical operations. Even when we are not directly writing complex NumPy logic, it is part of the foundation beneath Pandas, scikit-learn, and many model workflows. Understanding that modern AI systems are built on numerical computation helps demystify the field. Models are not magic objects. They are mathematical systems operating on structured numerical representations of data. Scikit-learn will become our main library for classical machine learning. It gives us a clean and consistent way to train regression models, classification models, pre-processing pipelines, and evaluation workflows. For the first predictive parts of the course, scikit-learn is exactly the right level of abstraction. It lets us focus on the core engineering flow, prepare features, split data, train a model, evaluate performance, and make predictions. Later, we will introduce PyTorch. PyTorch is a deep learning framework used to build and train neural networks. It becomes especially relevant when we move beyond classical machine learning and start discussing tensors, neural network layers, training loops, checkpoints, and model artifacts. PyTorch is more flexible and lower level than scikit-learn, which makes it powerful, but also more demanding. That is why we do not start there immediately. We first build intuition with simpler tools and then move into deep learning once the surrounding workflow makes sense. Another important concept in this chapter is environment isolation. Each project should have its own controlled environment. This prevents one project's dependencies from interfering with another project's dependencies. Whether we use Venv, Conda, UV, or another environment manager, the principle is the same. Dependencies should be explicit, reproducible, and local to the project. A machine learning solution should not depend on random packages installed globally on a developer's machine. Version control is also part of the workstation, not something separate from it. Git gives us a way to track changes to code, notebooks, configuration files, and documentation. In AI projects, this matters because the work is experimental by nature. We may try different features, compare different models, change preprocessing steps, or adjust evaluation logic. Without version control, it becomes difficult to understand which change produced which result. This is especially important when notebooks are involved. Notebooks are excellent for exploration, but they can become messy if treated as disposable scratchpads forever. A disciplined workflow keeps notebooks understandable, names them clearly, commits meaningful versions, and gradually moves reusable logic into normal Python modules when the solution matures. The workstation also needs a practical approach to secrets and configuration. API keys, database connection strings, cloud credentials, and access tokens should not be hard-coded into notebooks or source files. Even in a learning environment, it is better to build the right habits early. Configuration should be separated from code, and sensitive values should be handled through environment variables, local configuration files that are not committed, or proper secret management when moving toward production. Hardware matters, but it should not dominate the conversation too early. Many machine learning workflows can run perfectly well on a normal laptop, especially when working with structured datasets and classical models. A GPU becomes more important when training larger neural networks, working with images, using transformer models, or running heavier inference workloads. For this course, the important mindset is to start with a workstation that is reliable and understandable, then add acceleration when the workload actually requires it. In our real estate valuation platform, the workstation becomes the command center for the whole solution. We will use it to load property data, inspect and clean the dataset, engineer useful features, train models, evaluate predictions, store artifacts, and later build an inference API. The same local workflow becomes the foundation for everything that follows. If the local environment is chaotic, the later production architecture will also become harder to reason about. By the end of this chapter, the student should understand that tooling is not a side topic. The workstation shapes the speed, quality, and reproducibility of the entire AI workflow. Python gives us the ecosystem. Jupyter gives us the interactive laboratory. Pandas and NumPy help us work with data. Scikit-learn helps us train classical models. PyTorch opens the door to deep learning. Git helps us track change. Environment isolation keeps projects stable. Configuration discipline helps us avoid fragile and insecure habits. A senior engineer should remember that successful AI engineering is not only about choosing models. It is also about creating a workflow where models can be built, understood, reproduced, improved, and eventually deployed with confidence. This chapter gives us that foundation before we move into the next major phase of the course, data collection. Thank you for watching this chapter. I hope you found it useful and learned something valuable along the way. If you enjoyed the course, please like, subscribe, and support the channel. It really helps me create more content like this. For additional chapters, complete training paths, and other technology courses, be sure to check out the Opus Magus Academy channel. And if there are specific topics, technologies, certifications, or courses you would like to see covered in the future, please leave a comment below. Thank you for your support, and I'll see you in the next chapter.